tough realities, the technologies. Biofuels. I hope the preceding section has presented a reasonable case for the imperative to move in the direction of renewables. Having said that, I'm quick to point out that most of these discussions are not at all black and white. In particular, a professor at MIT is soon to release a paper pointing out that CO2 is a significantly weaker greenhouse gas than was previously believed, and that increased concentrations in our atmosphere will be likely to cause only a fairly small increase in the Earth's surface temperature. But what will be the effective forces that could serve to accelerate global warming, like the melting of the Arctic permafrost and the resulting release of the methane under it? And what about the reduced concentration of aerosols? Let's be honest. No one knows. To say, the debate is over seems very foolish and wrong to me. What? You don't want to be confused with facts? I think rational, unbiased people have to acknowledge that there is a debate on the severity of the problem here, a debate that is composed, unfortunately, of 10 parts bombast and power politics, to 1 part honest science. The oceans are a huge sink for CO2, and serve to mitigate the increase in the rise of CO2 levels in the atmosphere, even as we continue to destroy the rainforests and burn hydrocarbons. Of course, this comes at the expense, most believe, of increasing the acidity of the oceans, damaging the development of shellfish and the entire ocean ecosystem. Exactly how much? Again, no one knows. Other recent developments include the idea that some, or even most, of the oil on the planet is not fossil fuel, but was made abiotically when the Earth was formed. What will be the result in terms of the availability of oil and natural gas? We recall that Matt Simmons said, "It's unclear if we're running out of oil. But we're certainly running out of cheap oil." If there are huge natural reservoirs of such hydrocarbons very deep under the Earth's surface, how does it affect the discussion? Once again, it's anyone's guess. We need to deal with the fact that there will be ongoing controversy about the effects of extracting, refining, and consuming carbon-based fuels. But here's a point to ponder: our rates of childhood cancer are going through the roof. Does anyone have a suggestion for the cause, apart from the fact that our way of life here has become so completely unsustainable? Additionally, in terms of the geopolitical and macroeconomic elements, consider these hard facts. As of December 2002, when the military pre-planning and pre-placement of ammunition and troops in preparation for the Iraq War had begun in earnest, there were about 972 billion barrels of total oil reserves in the top 16 oil nations. Of this total, 69.98% was inside a turbulent Middle East, a mere 12.64% was in the Americas, South and North combined, and only a piddling 2.33% was here in the U.S. Over 80% of the world's oil reserves are within the territory of the top 16 countries. Here's a 2002-03 breakdown of those 16 countries' oil reserves from the U.S. DOE. Rank country billions of barrels reserve percent of the top 15. 1 Saudi Arabia 261.8 26.93%, 2 Iraq 112.5 11.57%, 3 Kuwait 98.9 10.17%, 4 United Arab Emirates 97.8 10.06%, 5 Iran 89.7 9.23%, 6 Venezuela 77.8 8.00%, 7 Russia 60.06.17%, 8 Nigeria 32.03.29%, 9 Libya 30.03.09%, 10 China 23.72.44%. 11 USA 22.72.33%, 12 Qatar 19.62.02%, 13 Algeria 13.01.34%, 14 Mexico 12.61.30%, 15 Norway 10.31.06%, 16 Brazil 9.81.01%. Note, Canada has 180 billion barrels of reserves, but 174 billion are locked in tar sands, and extracting it is highly inefficient and expensive. With approximately 4.6% of global population, we here in the U.S. currently consume just short of 20 million barrels of oil a day. That's imports and domestic production combined. We gulp it in for our agriculture, transportation, industry, electricity generation and home heating, in the form of various fuels, petrochemical fertilizers and pesticides. We also use it as raw material for a wide range of plastics, solvents and medicines. At that furious rate of consumption, if we are ever bereft of foreign oil, our domestic 2.33% signifies an interval of less than 3 before we consume all U.S. reserves. The two most populous nations in the world, India and China, each have over 1 billion people. They're chasing our consumptive lifestyle and our infrastructure at a breakneck speed, and oil simply cannot be sucked out of the ground fast enough to slake that thirst. We now come to a set of interviews on a few of the popular technologies that represent the constellation of renewables at this point in our evolution. Again, I was lucky enough to have found subject matter experts who, I believe, did a great job of articulating the basics issues of their chosen area. We begin with Dr. Gregory Mitchell, research biologist and senior lecturer at the Scripps Institution of Oceanography, one of the oldest, largest, and most important centers for ocean and earth science research, education, and public service in the world. Dr. Mitchell was good enough to speak with me about the use of algae as a biofuel. Craig Shields, thanks so much for helping with this chapter on biofuels, Dr. Mitchell. From a high-level perspective, we're converting the chemical energy that was ultimately derived from the sun in the form of high-energy carbon bonds, and we're breaking them down, burning them for instance in biodiesel, and converting that to kinetic energy. Is that essentially right? Greg Mitchell: yes, that's right. Fundamentally, the photosynthetic process reduces inorganic compounds like carbon dioxide, water, nitrogen, and phosphorus, and builds these biochemicals. Initially sugar, and then the sugar is burned to build all sorts of other things, and nutrients are brought in, and you build membranes with phosphorus, and you build proteins with nitrogen and so forth. So yes, it is all ultimately derived out of the sunlight. Then, if you dry out any organic matter, you can burn it. You take plants, cow dung, etc. So that's called oxidation, of course. It's a cycle. You take oxygen and water and inorganic carbon dioxide and nutrients, and you use solar energy to push them up the energy chain. Once they're up there, they have potential energy, and then if you oxidize them, which is effectively burning them, then you bring them down. Mammals' warmth comes from the slow burn of these molecules that releases heat, and then we insulate ourselves and hold on to that heat to be warm. So yes, you've pretty much got it right in that regard. What people need to understand is that petroleum, coal, and natural gas are the same category of thing. They are biofuels. They are carbon, organic carbon, fixed in some ancient time, usually between 10 million and 100 million years ago, fixed by the same photosynthetic process that we're talking about now for biofuels. If you really think about it logically, They're all biofuels. So there needs to be a clear distinction between biofuels derived out of the contemporary atmosphere and then reburned into contemporary atmosphere and biofuels that derive CO2 out of an ancient atmosphere and then stored it away in a geological reserve and then is exploited and burned into the contemporary atmosphere. It's just that now we have the carbon cycle disrupted by our burning rapidly a huge reservoir that was put down millions, tens of millions, 100 million years ago. So we're burning it at a pace far faster than it was ever laid down geologically. That's what's causing the imbalance in the atmosphere. CS, okay, that makes sense. GM, so, now the kind of question is, well, can we cut that time cycle short? Can we just take the solar energy now and use it? Of course we can. We can and we do. Of course, people have chopped down trees and burned them throughout the millennia, and that's one of the big reasons the Earth's becoming deforested. So not only can we do it, but we have to ask what are the environmental impacts of what we do now, and what are the unintended consequences. If we just start cutting down all of our forests to replace petroleum, now we deforest the land and we've got other problems besides the fact that we are buying petroleum from countries that don't like us very much. It's very complicated. So where do you start? I think the first thing you do is you ask questions. What do we humans need to survive? So, everyone's saying, well, we need energy, and that's true. It's very clear that industrial capacity, standard of living, educational levels, are all proportional to the rate at which any nation consumes energy per capita. A nation like Japan or Europe might be much better than a nation like the United States in terms of having a similar achievement level economically and socio-economically, and yet utilizing less energy. But California is on a par with them. We've got 30-something million people in California, and we're on a par with all those other nations. But there's other places in our nation that aren't on the same par, like Texas, that are farther behind per capita. This relates to policy. So we do need energy, and energy drives our economy, and we need food. The second one I'd like to stress that people don't pay attention to that much is that 80% of our agriculture is to feed our animals and 80% of water use on Earth is for agriculture. So something like 60% of our water use is to feed animals. And if you start looking at energy, which is, I think, the overall premise of your book, right? CS, exactly. GM, you need to look very closely at the consumption of energy for agriculture and for pumping water. In California, about 30% of our electrical use is to pump water, and more than half of that is for agricultural and irrigation and distribution purposes. A big part of that energy consumption is to pump water over hill and dale to get to the sewer plant to throw it away into the ocean. So there's all sorts of ways we could go upstream and not pump over hill and dale and process our water back to potable water reuse, or certainly irrigation water, and pump less and save water. If you save water on the front end, you're using less energy on the back end. My point is that the biological cycle and the water cycle and the nutrient cycle and the CO2 cycle are all the same thing. They're all driven up by sunshine, and then it's all degraded back, mostly by bacteria, to inorganic nutrients. That cycle goes around and around, and so when you start talking about energy, or bioenergy, you have to talk about water and nutrients. And you have to talk about CO2. They're all linked. I think you could go to an ecology textbook 101 and you can see that water, inorganic nutrients, and sunlight make the organic molecules we talked about, and that respiration brings them back down. The fact that it's a cycle suggests that we can proceed into the future to try to tighten that cycle up as efficiently as we can, locally. So, when you get back to biofuels themselves, what's the question? What do we really need? Well, we need energy. Biofuels are in everybody's wedge of how we are going to replace liquid petroleum. If you look at the requirement for liquid fuels into the future, every oil company and every nation in the UN has a biofuels wedge growing. At last year's annual meeting at the American Association for the Advancement of Science, AAAS, the talk about biofuels was depressing. If you were going to fill that wedge by 2030 or 2050 like is in everyone's chart, you're going to destroy the earth. You consume the water, the rainforests are going to go, you just can't do it. There's not enough land to do it with traditional agriculture. But your question to me is about biofuels. We clearly need to produce food with sunlight through photosynthesis to feed our animals, or else we should all become vegetarian. And we could all become vegetarian. That might be useful, but I'm not sure that the 2/3 of the planet that's not vegan wants to become vegan. Animal protein is important for most humans. So now you get to the question of efficiency. Here's a third main point I'd like to make. The solutions can only be achieved if we create wealth in the economy. In other words, you can't just tax the existing wealth base and solve the huge problems because the costs of the solutions are so huge. They have to pay for themselves. When you ask, what can pay for itself? That sounds difficult, but fundamentally you look for efficiency. So that takes you to algae, and also cyanobacteria, which are actually a form of bacteria that are photosynthetic, so I'll refer to these collectively as algae, photosynthetic organisms, mostly the microscopic ones because they're super efficient at growing, at taking up nutrients and CO2 and creating biomass with sunlight. The microscopic ones are more efficient, faster growing than the larger ones. You go small. This class of organisms, photosynthetic microorganisms, can produce biomass 10 to 50 times more efficiently than any terrestrial plant, and they can produce protein on that scale, 10, 50 times more. So in other words, if you have a soybean field, you can produce about 10 times more protein per acre per year growing algae or cyanobacteria and about 50 times more biofuel molecules. So right now, soybeans are mostly grown to produce pig food and chicken food. You know, they press the soybeans and the soy powder is pretty high in protein and it feeds our animals. And the residual oil is available for biodiesel. So, if you have something that can achieve 10, 50 times these yields, any industrial economist looking at creating wealth, if you find something that's 10 or 20% more efficient, they chase it with billions of dollars in investment to beat the competition. Here we have an agricultural possibility that's 10, 50 times more efficient. And not only that, Craig, but these systems can be laid out on non-arable land, so you don't have to worry about topsoil. You can grow them with saline aquifers or seawater, and so you can perhaps minimize the land impact and otherwise food for fuel debate because you set it up on land that's not otherwise suitable. And you also eliminate that debate by using seawater or saline aquifer water that you can't irrigate with or drink. So these are huge advantages. CS, wow, no wonder people are so excited by all this. GM, right. And for this reason, society needs to invest. Now can we make a profit on it tomorrow? No. But if you're going to go down this road, if you really do explore the cost of energy for agriculture, what you're going to realize is if we make algae our solution for pig food and hunger, then actually, we're going to save a huge amount of energy and water. To me, and this is my last, most important point, I think that is the most significant driver, and not fuel. It's animal feed, which if you look at the economics of algae, it turns out that the best you're going to do in terms of biofuel molecules is maybe 30 or 40% of the original biomass. It could be into a diesel if it's a vegetable oil, which most people are chasing with algae. It turns out algae can also make a lot of carbohydrate, and you can go down the biobutanol path or ethanol path or other path that would derive out of carbohydrate. So you don't have to be exclusively into the vegetable oil diesel kind of a product. You could also be into the biobutanol or ethanol types of pathways as well, with different kinds. Now it depends on which algae you grow. So, that might be 30 or 40%, but what's the other half or so? It's protein. And that protein is what we need to feed to our animals in addition to some Bermuda grass or whatever the farmers grow. So the point is that we might be able to offset a vast amount of agriculture with much less area, and that gets back to your question about how much area do you want for solar panels to get all the electricity. The same diagrams exist if you look at, let's say, replacing all of the US diesel by corn. It takes up the entire United States. We are replacing half the US diesel, and this is the line I got from Chevron. Half the US diesel from corn would take all the United States. Half the US diesel on soybeans, which produces more oil, would be like a third of the United States. And half the US diesel on algae would be this little tiny snippet in Arizona somewhere. CS. Wow. This as well came from Chevron? GM, right. This diagram is from them. You know, they have it. Exxon has the same diagram. All the big oil companies are looking at this. It's economics, I think, Craig. An investor's going to invest right now because he thinks he can make a profit in 3 to 5 years. And we are not at the point where the algae production systems are efficient enough, that we know how to do it well enough, to actually make a profit right away. Although some companies say they are there, my personal feeling is that if they are there, then they should be making billions of dollars a year. They're not there yet. But some of them may be close. From an engineering production scale point of view, it's clear we have not done it yet. But if you think it's impossible, it's not. Going to the moon looked impossible, but we did. There's no reason why we can't. There's no reason humans can't do it. If it's a scientific breakthrough required, there is possibly a major impediment, but I don't see the scientific challenge. We know the growth rates, the yields. We know these things. There are interdisciplinary problems of all sorts, but I think it's a matter of putting it together and engineering it. CS, what would you say are some of the engineering challenges? GM, there really is a lot of work aimed at making the right decisions, at least a dozen. It's everything from strains that produce the biomolecules of interest and can be sustained in a high-density mass culture without being invaded by something else that takes over and not getting attacked by bacteria and viruses and suddenly just crashing on you in ways you don't understand. These things relate to the organism of choice. We need to find elite organisms that work. In other words, not everything works for terrestrial agriculture. In fact, surprisingly few plants on Earth have ever been domesticated to make a huge difference. You know, we have corn, sorghum, soybeans, whatever. There's a huge number of plants on Earth, but not that many of them have really been domesticated. So we need to find these elite organisms that are going to perform super well, and then we need to have systems that are very low cost that we grow them in. we have to bring the production cost down by a lot. So that's an engineering challenge. Then the next challenge is, though it's probably not as significant, separating the algae from the water. There is a lot of energy associated with moving water around, so we really need to find very efficient ways to pull the algae particles out of the water without spending too much energy. That's sort of the harvest step. Once they are harvested in high concentration, you've got to bust the cells up. You've got to extract the molecules of choice, you've got to separate things, and process them, refine them. Once you concentrate the material out of the water, then it becomes basically the food processing and petroleum refining industry and the beer industry. They know how to deal with these kinds of things at the downstream. So I actually don't think those will be that big of a problem. I think it's the front end, which is the elite organisms, bringing the production systems down substantially, and finding a very low energy way to harvest. CS, didn't I hear something about an ostensible breakthrough in algae recently, feeding plants macronutrients instead of just exposing them to sunlight directly? GM, yes. There are companies like Solazyme that are talking about growing algae in fermenters with organic molecules. And there is another company named Martech that already has a large business fermenting algae to make polyunsaturated fatty acids that go into baby food, for example. They're putting the stuff in there because it's good for brain formation for babies. They have a $300 million market selling high-value products. Pretty much almost anyone I know in this business believes that fermentation of algae to high-value products is certainly viable for an industry like Martech, maybe Solazyme, but I don't see how you can go to scale for fuel for that. CS, that makes great deal of sense. So what needs to happen to move this industry along? GM, this is where the public has to come in and back the research to get us there. How did Brazil become an ethanol economy? It was a major commitment by the public. The government made a decision to do it, and they did it. It took them 20 years. So is our government or any other government going to make that decision about algae? I would strongly recommend it. CS. Fascinating. It goes back to the crux of this book, looking at the practicalities and the impediments. In other words, there are technological, there are financial, and there are political impediments in each of these areas. I would think the people in traditional energy with the drill, baby, drill mentality don't like this. GM, well, drill, baby, drill is a misperception that there's somehow this opposing dynamic. The charts from the oil companies pretty much accept that they're going to be able to produce about 100 million barrels per day. Even if they drill, baby, drill, they can produce more than that, but demand will go up. We can't fulfill the demand that society is going to put on the overall economic system, and there's also these major climate challenges, so we have to do two things. 1. Is create alternatives that will fill in the demand because there are 6 billion humans on Earth and only 1.5 billion actually live relatively prosperously, consuming lots of energy. The other 4.5 billion have growing aspirations. This demand won't go away. No matter how much you drill, baby, drill, you're not going to exceed a certain maximum and then you still are going to have demand above that. So I think what all these oil companies are looking at is we're going to have to fill this wedge in, and biofuels are the wedge. See what I'm saying? CS, absolutely. But how do we get from here to there? GM, the impediments are similar to those that are in front of various emerging technologies. Let's just take the broad-based desire to develop a biofuels industry in the United States, in part for security. It doesn't have anything to do with the environment, it really has to do with security of our liquid energy supply. And so there are tens of billions of dollars, somebody told me it's $20 billion a year of subsidy for corn ethanol. Okay, well everyone knows the corn ethanol is bare minimum, break even, in terms of CO2 and greenhouse gases, maybe even negative. In other words, you produce more greenhouse gases than you offset. And everyone knows that you can't do it cheaply enough to equal petroleum. You've got to have a subsidy. If we invested the amount of the corn ethanol subsidy in algae, we would create sufficient scale to drive the cost down by about a factor of 5 to 10 from where it is now, which would be huge, because then investors would start chasing it. But there is a lack of knowledge of the potential and a lack of confidence that public policy investment, which means money, would truly overcome the hurdle. So one of the impediments is a perception among the politicians, which means a perception in the public. The public doesn't understand it. That's the role you play, Craig. I really think this is one of the most significant impediments, the lack of knowledge of the potential, and the lack of commitment by the public to endorse this as a substantial option that should be done. But here's the root of the issue. Suppose we create public understanding. But you know what? There is no economic constituency for algae. There is for corn and soybeans. So now you go into policy. No matter what the public believes, the policymakers are listening to where the jobs are, right? There are no jobs in algae. We don't have industry. So that becomes a huge policy impediment. CS, how is that, though? If you're using non-arable land, and you have all this other good stuff going for you, isn't there a legitimate trajectory for jobs? GM, there are a lot of jobs to be created in a 10-year time frame, but a politician's lifetime is not 10 years. It's 2 or 3 years. So they can satisfy a huge number of constituents right now that depend on soybeans or biodiesel infrastructure for corn or tractors, all these things that relate to traditional agriculture. So there is not a large industry that's built around algae, and in the first 5 years it's going to be a relatively small numbers of jobs. CS, I see. This political cycle seems to be a recurring theme in the interviews I've conducted. GM, I don't doubt it. I think that the real impediments are going to remain forever if the public and the policymakers don't get on board. So I actually think the biggest impediments are the public and the policymakers, and then, if we have the funding for 10 years, and the patience, a highly mature industry will follow. CS, great. Let me ask you about the allocation of funds under the stimulus package. Has algae received anything at all? Obviously this goes back to the subject you were talking about a couple minutes ago. But what percentage of overall kind of renewable energy dollars have you received? GM, I don't know the percentages, but I do know there is substantial money that is now moving into the algae space. And that's a blessing. I mean, there's been nothing from the US government for decades. It's been shameful. I think we need a lot more patient money. We need to train students, taking the biology with the chemistry and the engineering and the physics and building systems and working together in an interdisciplinary fashion, not just to commercialize, but to solve all the problems. To work hard on the problems, put graduate students to work. Then those students would come out in the industry. We really need the front end of the discovery and the interdisciplinary research, and that needs to be a little bit more patient than a commercialization thing. It's got to have a 10 to 15-year vision. CS, that makes sense. It's funny because, As I conduct these interviews, I try to look for common threads, and that is certainly one. Let's figure it out before we start. Let's not ready, fire, aim. GM, right. If you look at photovoltaics, we've been investing huge amounts in photoscience and photovoltaics for decades. If you look at any agricultural thing, there's a huge number of agricultural industries around, universities around, huge industry, huge numbers of jobs already, petroleum refining, you name it, any industry you can think of, there is a pretty decent balance between experts in the industry and experts in academia. But if you look at algae, there are no experts in industry because there's not an industry. This will require patience, but the payoff will be enormous. CS, I have to believe you're right. Thanks so much for your time. For more information on this contributor, please visit http://2greenenergy.com/ renewable-energy-facts-fantasies/